Okay, so let's see. So the topic for today, which I'm going to talk about, is physics-informed neural nets. So let's see what it is, or you might say physics-assisted or guided neural networks, or deep learnings, or AI, whatever. So let's start with deep learnings. All the method that we learned so far actually is based on data-driven approach. Assume that we have a bunch of or some amount of data set. We want to extract some knowledge or hidden knowledge or information out of it. Of course, there are pros and cons, and speaking of advantage of that is that here you can see that if we do have enough data or enough data is available, so that's the condition that we have. We have to have some the good quality of or good amount of data. We make them available already. Those are going to be the materials, and then the legitimate level of prediction performance or classification performance or estimation or prediction performance can be achieved without any domain knowledge. Right? That's the kind of general statements. And I guess most of you kind of agree with the statements. Here, actually, key thing is without domain knowledge. Right? That's kind of the data scientist perspective. They say that, hey, I'm not expert. I don't have any domain knowledge, but if you give me like enough data set, I can do something. I can give you some useful information or knowledge that we can extract it from the data set that you gave to me. Okay. And we learned like how, right? Starting from machine learnings and deep learnings and a lot of different topics that we have been covered so far. And this one is kind of illustrations. We take the supervised learning as an example, say X and Y. So you can think of X as input, and the Y is output or predicted values. So again, give me the X, I can give you Y. But in order to do that, I have to have some paired data set, which is X, right, for supervised learning case. And using that training data set, I can build up some models, data-driven approach models. This could be like one of the deep learning networks or machine learnings or logistic regressions or linear regressions, whatever, or SVM or ANN and CNN. It really depends on the type of input and output data set which is available to us. But the problem is, or the issue that we never did is, it's a black box. We have no idea. I would say we do some kind of computations and train, so we learn the models. That means we will get, if that's the deep learning models, we will get all the weights and bias. That's the structures, that's something that I'm going to design. So I know structures of deep learning networks, and after the training process, I can estimate or I can compute weights and bias That's all we think that we know. But out of that, it's kind of difficult to see, understand, or to see what's happening inside. What's the mechanism of predicting Y given X? You can think of it as it's almost black box. We have no idea what's happening inside the approximated functions, especially when you're talking about deep neural nets. So that's kind of the disadvantage, or one of the biggest disadvantages out of data-driven approaches, you might think. So since that's kind of, we treat it as a black box, and there are a lot of disadvantages and so drawbacks, and some of them that I can illustrate here is it's a lack of interpretabilities. Again, like I said, we have no idea what's happening inside. We have no idea. We are not able to explain. Think about it, like MNIST data set we have. I mean, we have almost 99 or almost 100% like classification accuracies, but we are not able to explain why. I mean, the performance is good, but at the same time, it's a lack of interpretabilities. I mean, that's not, I don't like it, and most of the like engineers, the people don't like. So we want to understand, but somehow it's not easy, it's difficult. I mean, that's why you learn in one of the topics is explainable AI, right? And the second issue is that we have is generalizability. It's lack of generalizabilities. It means that, okay, we say we do have some training data set, and hoping that we are able to build the good models to represent these given training data set. And if we have another data points, I mean, within the data distributions, or we might say like interpolations, within the data sample within the data distributions, the training data, distribution of training data set, that prediction, I mean, the performance is, we kind of say it's going to be okay. But in many cases, we might want to have, say, suppose we have, this is the data points, and we want to know what will be the outputs, which the deep learning model is going to estimate it, but it's extrapolations, not interpolations. But it's not natural to expect that your trained deep learning models gonna have a good prediction performance on the extrapolation data points. So it's really risky. And what's the cross domain means that suppose you want to monitor some kind of machinery in your factory, say you had the same machines, like mechanical or machines, you said you have 10 of them, or you want to apply the anomaly detections. So you randomly pick one of your machine, and you collect or gather the normal data set, and you say you are successfully able to construct anomaly detection models. And you tested it with the same machines that your testing validation outcome was also really good. And you decide you want to apply the same models to rest of them. Okay. In general, I mean, training data set, you will get A machines, and you build up the AI models, apply machine B. You're not gonna get the good performance. So in that case, it's lack of generalizabilities. It really depends on the training data set. It really depends on your training data set. So those two are general drawbacks when we're talking about data-driven approaches. The first one is lack of interpretabilities, and second is lack of generalizabilities. Those are the issues we have. A lot of people trying to overcome from like statistic perspective or AI perspective. And one of the examples is like say the explain of AI. And second, like in order to make your model more general or robust, trying to get basically from the statistical perspective, you have to have more and more data set. So like data augmentations and self-supervised learnings, those kind of things. But what I'm trying to say here is that, hey, I know these issues that I want to overcome. There are many ways, but what I'm trying to share with you is that I want to build up the models, not only based on the data set, but also physics, the governing physics of that systems or applications that you might interest. If the knowledge of physics is available, we call it physics guided or physics informed AI. I mean, again, AI is data-driven approach. I mean, there's no physics, has nothing to do with the physics. But we want to embed it, knowledge of physics into AI model or into data-driven approaches or method. That's what we are trying to do. Why? Because we're hoping that we kind of overcome those the drawbacks. Okay? So, in the direction of AI or deep learning models, here I said in mechanical engineering, but in general engineering in field, is that somehow I want to try to combine or hybrid AI with in domain knowledge or mechanical. For example, it's here in the mechanical engineering. So for illustrations, say we have same data-driven AI models, have X and Y. We're trying to build up the networks in the middle. And what if we do have some knowledge of the system that so in many cases in dynamical systems, it doesn't have to be in mechanical engineering, but say there's any related engineering problems, many of knowledge or dynamics or physics will be represented or expressed by some of the partial derivative, right, equations. I mean, this is one of the examples. So the idea is that what if the governing equations or dynamics or physics or some kind of prior knowledge is available apart from the data? Okay. So from data analytics or data scientist or AI guys' perspective, say if you have pure data-driven approaches, since your system here and governed by these equations, and since we don't know any physics, we assume that we have no idea. But the input output as a training data set governed by these physics, right? So from data scientist perspective, if X and Y, enough of them is available, they believe that they are able to extract these physics knowledge as well. But from like engineering perspective, like me, I mean, those are the like prior knowledge is we already know. We don't have to ask AI models try to learn these things from scratch. Pretend we have no idea. For me, it doesn't make sense. So I'm gonna induce, or I'm gonna reinforce the AI models that these are the knowledge that I know that, so you don't have to learn it. Just trying to follow that. That's the kind of the philosophy behind physics-informed AI models. That's okay. So I'm gonna give you like another explanations related to physics-informed AI models. Suppose we have 4 data points like that. That's the only data points. We have no idea those 4 data points where those differences they are coming from. Okay, suppose we have that kind of problems, and I want to estimate it. Say this is the x-axis. I want to estimate it what kind of values that we might have at that point. That's again, it's a regression problems or prediction problem, or if it's time t, so it's going to be prediction. In x, it will be estimate or regression problems. And I guess it's not that easy, not that difficult to see that the best thing that we can do this is going to be the best approximated, right, out of training data set, right? That's the best thing that we can do because we don't have any other informations. So that's reasonable that data points around here will be like that. I mean, that's again the best thing that we can do. But what if suppose we do have another knowledge on the system that we are interested in. What is this? What is that? Have you ever familiar with that? We have M and K and X double dot, and that's like a mass and spring systems, right? Like, what if we have and if you recap like what you learned from like dynamics or vibration class. Suppose somehow or somebody told us that that's the governing equations. And this is the data points that we collected or measured, whatever. And this one, of course, again, it has nothing to do with the data points. That's kind of the pre-knowledge that we have or available. And we know that that's kind of the differential equations that represent spring mass without damper, like oscillating, vibrating something. Then if we do have this knowledge, probably instead of estimating like that, this one could be, because somehow we know that it's oscillating like that. So what I'm trying to say is that knowing this, and these are totally different. Again, if we know that, probably here, this could be the more reasonable predictions or estimated values out of it. Why is that possible? Because we do have additional or another information related to the system or related to physics of that system. Okay. And if we have, I mean, the oscillating, this one could be another representations, and this one could be another. But you know that in differential equations, in order to get the exact solutions, we might need extra information, which is like boundary and initial conditions, things like that. So suppose we do have another information, boundaries or initial conditions, or more data set, like that, then the final answer is going to be like this one. Does it make sense? So let's think about all the data or informations that we have in order to finalize or confirm that these are the functions. We have 4 or 5 data points and physics. And the conclusion I was in this one, instead of having that, we will get totally different approximations. All right? Does it make sense? Does it make sense? And so when you go back to the issues that we have, interpretabilities, probably we might have, since we have more information or physics, now we know that it's oscillating. And this another issue was that it's generalizabilities, and since we know the physics, we can estimate it like any data points. It doesn't have to be interpolations. It could be, we can use that the models to estimate it, the extrapolations as well. I mean, if we have only 4 data points, it might be okay to estimate what kind of values, but if someone asks what would be the estimated values around here, it's really risky to might say these are, because we have no idea what's happening outside. So these are the data points that is available, and it's kind of safe that it's talking about data points within the distribution of training data set. What about the outside? You have no idea. Does it make sense? I'm trying to convince you or give you the motivations that why, even though we learn a lot of things related to data-driven approaches, still it will be better or be good if you have knowledge of physics or prior knowledge and add them together or combine them together. That's what I'm trying to say. So let's summarize and why still like deep learning models need the physics, and why the same thing is that why does the deep learning models or data-driven approach or black box model or method fail. There are a lot of different ways of say. The first one is that it might the output result looks okay, but physically inconsistent. Doesn't have to be consistent, right? Because it's a data-driven approach. Trying to do best approximations, but doesn't have to be physically consistent. Imagine you're dealing with some kind of physics problems, and the physics, like always, should be correct. The physics is not like something that we want to approximate it. It's always, you have to be satisfied or has to be true 100%. Or another way they said that this is the easy to learn space relationship that looks good. See, looks good only on the training data set or test data set. It's talking about generalizations. It's poor generalizations outside the available data set. It's talking about extrapolations. In generally, the performance is not as good as like the performance on the extrapolations is not like as good as the performance in the interpolations. So we call it within sample prediction task or versus the out of sample prediction task. Within sample prediction task and versus out of sample prediction task. Same as this talking about interpolations or extrapolations. To visualize it, let's think about this. So suppose we have time series data set, and in training, say the gray. So I want to build up the models with the function of time, any kind of models. Then in the data-driven approach to training, we have to have these the values in corresponding time index, and I want to test it or predict in red. In time perspective, the red is within sample, right? Within sample prediction task. But in many cases, in time series, we want to predict something. We want to predict what's happening in our systems in the future. So in most cases, these is going to be available for training. And I want to estimate or testing what's happening in the future. So these guys will be the out of sample prediction task. So again, I would say in general, it's not realistic to expect your data, whatever your data-driven approach is, the performance as good as in the case of out of sample prediction task. So you have to be careful. Again, like interpretability is absent. And if you think about a lot of engineering or scientific problems, what the deep learning model says is, give me the data set. I'm trying to give you some. I'm gonna give you some kind of functions, the approximated functions based on the data set. But in most of the case, if you ask yourself, what will be the final goal of what you are trying to do, is that you want to discovering the mechanism of underlying process. But the deep learning models, AI models, is not gonna give you such kind of answers for you. Because regressions or classification performances, although those things are good, doesn't give you any clue on why or how. So you have to think about it. You have to think about it. Whether the deep learning model is going to help you to understand or to increase the knowledge of physics that you are interested in. Okay, that's why I'm trying to, here I'm trying to share or show you the physics-informed neural net. We call it PINNs, PINN. The idea of that is trying to take full advantage of data science method or data analytics with the accumulated prior knowledge of scientific theories. Basically, we want to try to combine them together. That's the philosophy of physics-informed neural nets. So let's see more in here. The deep neural networks, there are many structures that we learned so far. Remember, we're starting with ANN and CNNs, RNNs, and this one is we're going to cover right after these topics. And generative models, right? Autoencoders and GAN, things like that. We learn a lot of different structures. That's AI models or data-driven approaches, several of them. And I kept saying like physics and physics and physics, but actually the physics is not like well represent all of them. It basically is a prior knowledge or some kind of knowledge outside of data set. So I'm gonna say knowledge representations. What kind of knowledge or what kind of knowledge representation is? The first thing is that, okay, so in many differential equations, there could be many of the physics or engineering problems or systems or applications can be represented or expressed by differential equations. It could be ordinary, it could be partial. You learn a lot of differential equations from other courses. That's not the only one. Or like algebraic equations. Right? That's another knowledge. It has nothing to do with the data set that we have. Or graph, knowledge graph. Or if you do the numeric or scientific computings, the simulations, you will get the simulation result. There could be another knowledge representations or human feedbacks. Right? We do have some kind of know-how which somehow we are not able to represent it in a mathematical form, but that's the knowledge, right? So, there are many of them here. There are many of them. So actually, the physics-informed AI model is, I'm going to say, prior knowledge-informed neural net. but I'm gonna say it's physics, as physics here is kind of symbolic like term for prior knowledge. Right? It could be chemistry as well. So it doesn't the limited to the physical problems. So those knowledge representations. And then the question is, how do you do the knowledge integrations? How do you embed such kind of knowledge into deep neural networks? So that's the key things that we want to know. I mean, there are several ways that we can do knowledge integrations. And the first one that I want to say is it's a feature engineering. What's the feature engineering? Say, given low data set, in order to make some kind of conclusion, it could be regression or classification problems. The first thing is that, like, you want to extract the useful features out of it. How do you do? You can do data approach. You can do like PCA autoencoders to extract good feature representations, or based on your experience or based on your knowledge, probably you might be able to pinpoint it. Hey, the feature is going to be good, and this one doesn't contain a lot of useful information, so we can get rid of them. Right? That's what I guess. This is the most effective way of knowledge integrations into data-driven method or models. So I would say most of you guys already doing the physics-informed AI models. Right? Feature engineering. So that's let me say this is the first one and the most effective way, I would say. And the second, I said design. What do you mean by design? Here, design the network structures or deep learning structures. So let me give you examples that we come up with. Suppose your data is image. Now since you learn the CNN models, you're gonna use CNN instead of ANN, right? ANN versus CNN has a different architecture or structures. Why you trying to do the CNN instead of ANN? Because you know that you are dealing with input, which is a type of image or matrix or tensors. That's the knowledge that you have. So you're gonna change your structure of your deep learning model. So that's designing part. You see what I mean? And you say same thing is that if you know the fact that your type of input data is time series. Now, since you learn it because you will do like RNN or LSTM structures instead of using ANN. Okay. And the last one, or third, is regularizations. You are regularizing. And this one, I'm going to explain it in more detail. So, what I'm going to cover so here in data-driven perspective, we do have a lot of models, I'm going to take ANN models. You can do similar things, CNN or RNNs, but I'm going to take it ANN as an example. Why? Because it's simpler. And for knowledge representations, I'm going to take the differential equations as an example of knowledge representations. Why? It's most common things, like differential equations. Right? For fluid or solid mechanics or heat, like thermodynamics or like heat transfer. You mean all the textbook you can find like at least one of the differential equations in those textbooks, right? And how to integrate the knowledge into the networks? I'm gonna show you how to utilize the regularization technique. This one you already know, and you already know. So that's why I'm going to take these three different components and show you how do you build up the physics-informed neural net models. All right. So let's move on to go further further discussions. I mean, I guess like you learn a lot of how to find the solution for the differential equations. Right? The freshman software probably trying to find the solutions by hands. Right? And junior seniors might be like, because in many cases it's too complicated or coupled, so that's why we try to use a computer to find the solutions, right? Numerical or scientific computings. What I want to do here is I want to use the deep learning models to solve or find the solutions for the differential equations. Do you think it's possible or not? So that's what I'm trying to show you. So it could be any type of differential equations. It could be from like vibrations or solid mechanics, right, or fluid mechanics, and pick any of differential equations and let's use the idea of physics-informed neural net, trying to find the solutions. You already know that multi-layer perceptron or the ANN or any kind of deep learning models are universal function approximator. Okay, there are papers like back in 1989. So there is a theory. It's a universal function, a universal approximating theory in this paper that is capable of approximating any functions. You don't have to know these. Like. And what is the differential equation? What are the differential equations? Like, you already know. Like type of operation. I mean the ordinary differential equations. It could be linear or non-linears, and PDE, like partial differential equations, like this. And these are kind of the mathematical expressions to showing the relationship among among the variables, right? And in trying to solve the final solutions, there are two like additional informations. The first is initials and the boundary conditions, right? And if all of them are available, we can find the solution. You know, in 1990, there was a paper saying that, look at the title, neural for solving differential equations. Right? And in 8 years later, similar ANN for solving ordinary or partial differential equations. And 2019, and the group of research from the Brown University and the Professor Kania Dakins In his group, he published the papers, say physics-informed neural net. Basically, he used a deep learning framework to solve nonlinear PDE problems. So basically, what I'm trying to do here is that follow what this paper says. In this paper, like, you don't have to know what it is. Say there's some the PDE Burger's equations, and here the exact solutions, and these are the red solid dot is predicted the values out of deep learning models, and as you can see, it's exactly the same. It's overlapped. Another example here is in Navier-Stokes equations. You might see in fluid mechanics. Instead of to scientific or numeric computings, you can use AI models to do similar task. So let's dive into what's the architecture of PINNs. How do you integrate the physics knowledge into deep learning networks? So this is going to be the kind of the most important. So we know that neural net is a universal function approximator, and suppose we want to estimate it like, let's see, you want to estimate any kind of the physical systems. We have X and T. That means it's going to have some dynamic changes or behaviors over time, and the X is a one-dimensional problem, and we don't know what function of F. And since this is some kind of functions, we can these are ANN networks to approximate function of F. Remember, these are input and output. Input for the network and input for the outputs. So basically, it's going to work as a universal function approximator. And if that's the given, that means it's a just data-driven approach. And what if we don't know what it is, but some kind of the differential equations, and we can call it those are the physical knowledge that we have and physical representations, and all the systems or data should satisfy that the conditions, right? Then, since and here you had, which is output of neural net. Of course, it's at the beginning of training process. I mean, it's not gonna same as you. But what we can do, we can compute this, and we can compute head, and take this, trying to, right? Because that's kind of constant that all the functional the U head should satisfy. How? That's the question that we have. So what we can do, so out of so again, let me say U head is output of neural net, and X and T is the input, and since this is universal function approximator, we're hoping that U head eventually is gonna same as U, but at the training process and it's gonna be different. But throughout the training process, we're hoping that, say we take the derivatives respect to t and respect to x twice, and now we can compute this u hat and derivatives, and initial conditions and the boundary conditions. It should satisfy some kind of initials and boundary conditions are gonna given. All right, and we wanted these u hat satisfy this constraint. How do you do? And remember, in training process or back propagations, if we don't have u hat and the actual values, like that's the loss function that we're defining, right? Trying to minimize it. That's the loss function that usually we define it. Now what we can do, we can add another term into our loss function. This one. We add extra term into, because we want to minimize this one. I mean, we take the squares, minimize, that means we want to make this one almost close to 0. So we want to minimize this and this at the same time. This one is data, right? Approximated, and this one is like measured data points. And this one is a physics. And of course, we have more than 1 or 2 terms in our loss function, so we might have different coefficient. It really depends on which one is more like important, things like how to penalize this. So these are kind of tuning or user-defined parameters. And we can add more, like we can add boundary conditions and initial conditions as well into your loss function. So your loss function is going to be multi-objective function in this case. I mean, I want to like, it's always 0 because that's the kind of physics and always satisfied it, but it's not. So instead of z equal to 0s, I want to minimize it. Minimize it. Does it make sense? So let me see. So here, another way that we say it is regularized by physics, but matched with sparse data set or data measured or observations or measured data set. I mean, if you add more terms in your loss functions or objective functions, we call it regularizations. So that's kind of basic ideas or basic architectures for PINN. You add extra terms in your loss functions, but those extra terms are going to relate it to your physics or initials and boundary conditions. I mean, say if we have different systems, have different differential equations, just change this one. Change this one. This is a typical structure of PINN problems. I'm going to skip this one. So a lot of research is let me see. Okay, so those are like a lot of different examples. You can find it like in Burger's equations and Schrödinger equations and 2D Navier-Stokes equations, and a lot of research already demonstrated using PINN, like so these are predicted, and this is the exact dissolutions or pressures, and see how similar each other. Another example is that I take it from the fluid mechanics, like Navier-Stokes equations. That's kind of the CFD simulations, and this one is the result or outcome from the PINN models approaches. Okay. So at least I can say there are a lot of research going on related on this topic nowadays. So let me show you the most, I would say the most advantage of using the PINN. Say, suppose we have this kind of problem. We have some two support and beam problems, and you might remember that it's in solid mechanics. That's the governing equations that, right? So that's governing equation for the beam from the beam theory. And suppose you put the sensors like that. And again, there are two approaches. The first one is that you can solve that the PD problems, or you can just, since you place the sensors on the beam, you can collect the data set. You can apply the data-driven approaches to estimate the displacement or the movement of beams. Or you can combine them together. And I'm just going to skip a lot of details, and I wanted to share the finer findings here. This axis is a number of sensors, and z-axis is the like performance or error speed. And let me see, the orange is a data-driven approach. So that means if you increase the number of sensors, that means if you are able to collect more and more data set, the accuracy, it gets better and better, right? Or the same thing is the errors get smaller and smaller. So it's always good or better if you are able to secure more data set. That's always true. But if you do have a small data set or sparse data set, the accuracy or performance gets worse. I mean, that's a natural for data-driven approaches, as you can see or expect. On the other hand, the physics informed, assuming that we know the physics related to beam theory, and although we have small number of sensors or small number of data points, the performance of accuracy is pretty much the same. This experiment's going to demonstrate it, how important to utilize the physics informations into data approach model. So reconstruct full displacement from the sparse measurement and embedding the governing equations into loss functions. So I want to summarize the concept of physics-informed neural net. Let's simplify the problems. And suppose we have big data set. If you have enough data, it might be okay to just build up the data-driven approach models without any physics into considerations. But suppose we have either some or small data set. Let's say if we have some kind of bean here. No, how I present it. Lots of data, small data, and how do you compensate these? Utilize the knowledge or information that we have from physics. That's the only way that, not only, but that's one way that we can do. So what I'm trying to say is that I'm pretty sure that in your research, most likely you end up having small data set over having the big data set. And here, probably you can try like data augmentations, or you might think, like, first thing is you might think, okay, hey, I want to do more experiment, or I want to run more simulations to increase the number of data points. That's first thing that you have to consider it. And probably second is, how do you overcome the issue of small data set, like say in a statistical way, like data augmentations and self-supervised learnings, whatever. The last thing that you have to think about it is that since we don't have, how do you overcome? Think about the physics, maybe. I would say knowledge, like prior knowledge that makes sense? And how do you integrate it? There are many, but I guess this one is the most typical way of combined physics into the networks. But that's not the only one. There are many ways that we can. There are many. Okay. So those are kind of the conceptual or high level of explanations, and we do have several demos related. Okay. So I'm just gonna show you what kind of problems that we're gonna attack. So the first one, the lab one, the first one is that I want to solve this ODE problem. What's the solution with these initial conditions? And this is this. If you think like something take the derivatives, it happen to be same as the cosine. It should be something like sine, right? We can solve it by hands, but I want to ask deep learning models I want to see whether this is possible or not. So that would be the simple, the first example that I'm going to cover it. And the second example, this one. Another example is I just took the problem from the solid mechanics and the beam bending problems. Yeah. So in this kind of bending problems, if you have this kind of external force distributions, and this is the governing equations, and you can think of a lot of boundary conditions and the boundary condition the other side, and these are the boundary conditions. And actually this looks complicated, but we can solve by hands, and this is the exact solutions. And assuming that we have no idea, and we're gonna use the idea of PINN, trying to solve it, and this will be the kind of, since we can make comparison because we know the exact solutions, and this is the predictive one. Is, you can see it's almost identical to the true. And the last example is we took example from fluid mechanics, Navier-Stokes equations, trying to solve. Suppose we have infinite plate like this. I mean, again, I know some of you might doesn't have any engineering background, but it's okay because you don't have to know all the physics behind. So in dynamic equations, it's going to be given, and initials and boundary conditions are given to you whenever you have a homework assignment or final exam. So don't worry about the physics here. All the information that we need to apply PINNs are going to be given. So we have this kind of fluid mechanics into the systems, and eventually you have like here, how do I say, the no slip conditions, and eventually your flow is going to develop like that. That's something, if you mechanical engineering students, something that you're supposed to know or learn from the fluid mechanics course. And these are the governing equations. And I mean, it looks complicated. I mean, that's the only thing that I want to give you, the impressions. You don't have to worry about what is the U and what is like the partial derivative of U of with X. You don't have to worry about anything, right? And this one is difficult to solve by hands. So actually, we ask another like computer simulations, and so this is the profile. So velocity of in x-axis and y-axis, and this is pressure. And we're going to assume that this is the true ground truth. And this is the we got from PINN, and actually you can make comparison between, and that's from the computer simulations, and this one is from AI. Again, it's velocity of x and y and pressure distributions. So what I'm trying to say is that I know you have different the backgrounds, and you learn a lot of things related to your domain, and such knowledge might be expressed some. Let me see. One of these, again, like I said, could be in the form of differential equations, algebraic equations, whatever. And throughout this semester, I hope that you learn something. And after this course, go back to your field and trying to integrate these two. Trying to integrate these two things. From data or from knowledge, combine them together. Okay. So I'm done with general explanations, and next week I'm gonna go over like how to implement it in Python. Okay, we have 3 or 4 different problems that we can try. Good. Okay.